Baghdad of the 9th century must have been a marvelous and exciting place. In the last lecture, we talked about the translation movement that took place largely in Baghdad, although in other centers as well, from about 750 to about the year 1000, where huge numbers of Greek and Persian and Indian texts were translated into Arabic. Now, in this lecture, I want to go a little bit further to talk about the contributions of Arabic authors themselves in the sciences. And we'll start with astronomy. Well, astronomy, as you know, was one of the high points of classical Greek science. Astronomical calculations, astronomical systems, cosmological speculations were all developed to a high degree in the ancient Greek world. Astronomy was also taken up avidly in the Islamic world, and Arabic astronomers made significant contributions. For example, one of the first books that was translated out of Greek was Ptolemy's Almagest. In fact, nowadays, we still use the Arabic title, not the Greek title, for the Almagest. That's how it was translated into Arabic. It's actually a compilation of a Greek and an Arabic word. You might want to keep an eye out in daily parlance for words that start with the letters AL. It's the Arabic definite article the, and so a lot of words in the English language that start with AL are actually of Arabic origin. Now, the importance of Ptolemy's Almagest to the Muslims, like to the Greeks, was only partially astronomical. It was also of astrological importance. I already mentioned how the date for the founding of the setting of the foundation stone of Baghdad was chosen astrologically. Well, in fact, the Almagest and Ptolemy's Tetrabiblos, that other work that has to be read alongside the Almagest, which is the key of what the astronomical positions actually mean astrologically, was also translated into Arabic. Arabic astronomers produced new star charts, improved methods for calculation of astronomical events, and calendrical reckoning. Now, if you go outside on a dark night, you look up in the sky and you pick out the brightest stars. To this day, about half of those bright stars have Arabic names, which is a constant reminder of the importance of Arabic astronomy and how influential it was in the development of European astronomy. Stars like Betelgeuse, Deneb, Vega, Aldebaran, Mizar, Algol, Altair, Rigel. These are all Arabic names. These were all names given to the stars during the Islamic Middle Ages, which were then transferred to the Latin Middle Ages. Many astronomical terms, in fact, are also of Arabic origin. The highest point in the heavens is the zenith, an Arabic word. The lowest point, the nadir, also an Arabic word, as is the azimuth, which is the angle between a celestial object and due north. Now, besides observing and calculating the heavens, the Arabic writers also designed and improved astronomical instruments. And the one astronomical instrument that is most important for the Islamic Middle Ages, as it would be for the Latin Middle Ages, is the astrolabe. Now, this is a cardboard copy of an astrolabe. The original ones would have been made out of brass, so they would have been much heavier than this. But the astrolabe is a remarkable device. It's used for observation, and it can also be used for calculation. So, for example, if I hold it up to the sky and use this called the alidad, again an Arabic word, I can sight through it to determine the altitude of the sun or a star. Why would I want to know the altitude of the sun? Well, if I know the altitude of the sun and the date, I can turn it over onto the back and use, I'll describe what this is in a moment, but use these sliding scales and this rule to calculate the local time from the position of the sun. I can also use it as a calculating device. I can figure out at what time on any day of the year any bright star or the sun will rise and set. I can also figure out astrological data, figuring out about the various houses and the position of the sun in them. Let me explain exactly how this works. The astrolabe is itself not an Arabic invention. It's a Hellenistic, Greek invention. What it is, it's a flattened map of the heavens. If we look here, and we can see on this surface these lines, which represent the lines of latitude and longitude in the heavens, as if we took the dome of the heavens and squashed them flat. Moving over that is this object called the rete, which is actually a Latin word, a net, which has pointers which allow you to line up where stars would be on that map of the heavens. There's then also this rule, which can be used to read off from the points of intersection of the stars with the band of hours on the outside to tell you something about their rising and setting times. So, a very useful device. You can calculate almost anything you want to know about astronomical times of rising and setting, local times, latitudes, using the astrolabe. One Arabic writer by the name of Ali ibn Isa was known by the epithet al-Asturlabi, the astrolabist, because he wrote so much about the astrolabe. The astrolabe not only was improved in the Islamic world, it was transferred eventually, as we'll see, to the Latin West, and astrolabes were in use as astronomical devices down until the 17th century in Europe. Even they existed alongside the telescope for a while. Other instruments that were invented were the Qibla finder. Remember, the Qibla is that direction towards Mecca. Well, if you're stuck out somewhere in Morocco or Spain or India, how do you know the direction to Mecca? Well, Arabic astronomer mathematicians devised little devices that you could carry around with you, which, using the position of the sun or the stars, could tell you the correct direction, allow you to calculate the correct direction in which to pray. Now, let me mention a few Arabic astronomer mathematicians in order to give you an idea of the scope of mathematics and astronomy in the Muslim world. Let me start with one that I've already mentioned. This is Thabit ibn Qurra, who was born in 836, died in 901. He was the Sabian. He translated and commented on a lot of works, but also did his own observations. Let me just mention some of his own writings. He wrote a commentary on Aristotle's physics, as well as a commentary on Ptolemy's Almagest and the Tetrabiblos. He preserved writings of Archimedes. Indeed, Archimedes came to the Latin West first through Thabit ibn Qurra's translation. Moreover, there are some treatises of Archimedes which are lost in the original Greek. And the only reason we have them is because of the Arabic translations, many of which were made by Thabit ibn Qurra. He wrote on parabolas and other conics, like Apollonius, the Greek mathematician, had done. He wrote tracts on all kinds of things. He wrote nearly 70 books. He wrote a work on why the sea is salty and proposed reasons for its saltiness. He wrote on music. He wrote on medicine. He wrote an exhaustive treatise on the construction and calculation and use of the sundial, which is widely used. He also did some observations which told him that the length of the Julian year, that is, remember the Julian calendar, 365¼ days long, figured out by Sosigenes the Egyptian for Julius Caesar. The length of the Julian year, Thabit ibn Qurra figured out, was off by 1 day in 130 years, which is an extremely accurate prediction. In fact, or not prediction, I should say, measurement. It's an extremely accurate measurement. Sosigenes' year was off by 11 minutes. And those 11 minutes are basically, out of the whole year, that's what Thabit ibn Qurra discovered. In fact, when the Julian calendar was amended in the 16th century by Pope Gregory XIII, this was one of the calculations that was used. Thabit ibn Qurra's work was pretty close, 1 day in 130 years. Now we use 1 day in 125 years is the correction of the Julian to the Gregorian calendar. That's pretty good. I should mention again that as a Sabian, his family was interested naturally in astronomical issues because the Sabians were basically star worshippers. And we find, in fact, that in the first generation of Muslim, or I shouldn't say Muslim, of Arabic-speaking, Arabic-writing astronomers, a great many of them are Sabians or come from Sabian families. So this is an interesting example of how a religious background can influence one's choices of what to study in the history of science, or what to study in scientific endeavors. Let me move to another astronomer, Al-Battani. Al-Battani was a little bit younger than Thabit ibn Qurra. He was born around 858, died in 929. He was certainly the best known of the Arabic astronomers in Europe later on when his work made its way to the Latin world. He was known as Albategnius in the Latin West. In fact, Al-Battani, under the name of Albatenius, was still being cited in the 16th and the 17th century as an authority. Copernicus, the great Polish astronomer, read Al-Battani and cited him. So clearly that's for 800 years his works were still being read. He made more accurate determinations of the lengths of the seasons. Remember, one of the problems with the old Eudoxian system was that the seasons are of different lengths. You can't divide the year into 4 equal points by the equinoxes and the solstices. In fact, the periods of the seasons are different, and Al-Battani clarified the lengths of the seasons. What he did also was to introduce trigonometry for the first time to the calculation of astronomical data. Prior to this time, the Greeks had always used geometry, and solely geometry. Ptolemy had the idea of the chord, which is akin to our idea of the sine, but that was only, he didn't really use trigonometry as we're familiar with it in calculation. That's actually an innovation brought into astronomy by Al-Battani. He made a lot of observations as well. He observed the differences, the changes in the apparent size of the solar and lunar disks. This allowed him to predict the possibility of such a thing as an annular eclipse. Now, he never saw one, and there was no record, as far as I know at least, of any of an annular eclipse ever having been seen. What is an annular eclipse? That's when the moon's disk moon is particularly far away during the eclipse, and so the sun's disk is larger than the moon's disk, and when the moon moves in front of it, you can still see a ring, an annulus in Latin, a ring of the sun around the moon, an annular eclipse. So he predicted that these were in fact possible, and he was right. He did observe a solar eclipse, not an annular one, at Antioch on the 23rd of January in 901. He observed a lunar eclipse at the same place a few months later. He also discovered the movement of the line of apsides. Now, what on earth is that? The line of apsides is the line that marks the place where the sun and the earth are furthest apart. If you want to think about it in the modern terms, it's the major axis of the elliptical orbit that the earth has around the sun. For them, it's the line that shows where the sun is furthest away from the earth. So think about it this way. We're standing here on an immobile earth in the middle of the universe. We watch the sun until it's at its furthest distance away from us, so its disk is smallest. It's receded into the background as far as possible. That line is the line of apsides, the line between the earth and the sun, and it must point at some constellation in the zodiac. Well, what Al-Battani recognized was that it wasn't always pointing at the same sign, because he had Hipparchus's calculations, Hipparchus's observations, which by his time were over 1,000 years old, and in that 1,000 years, that line had moved into a different constellation. And so Al-Battani was able to calculate that that line moved about 1 degree of the 360 degrees in the zodiac every 66 years. Clearly, he was a careful observer. He again commented on the Tetrabiblos. He made instruments. and wrote a large number of texts. Let me move on to my third character, Ibn al-Haytham. Now, he's known to the Latins as Alhazen, and that's the name under which he is most commonly called. He's yet a generation further on. He is 10th and 11th century, born about 965, died in 1039. Well, he did quite a lot of things. He criticized, for one thing, the disjunction between Ptolemaic cosmology and physical principles. Remember that there are some problems with Ptolemy. He moves the Earth out of the center of the universe and makes the orbits of the planets eccentric. He has epicycles where the planets are on this epicycle moving around a point on the deferent, and there's nothing at that point. And so there are problems when you try and relate the dynamics of physics of the time to the Ptolemaic system. They clash in certain places, and Alhazen was very sensitive to this and tried to work it out. He never did succeed in working it out, but he did start a discussion about this problem that continued in the Islamic world for several centuries. I should mention a little bit about his life, because his life is quite interesting. What does an Islamic scientist, if we want to use that slightly anachronistic word, do? Well, we know a lot about Alhazen's biography. Some things are contradictory, but nonetheless, I'll give you sort of a compendium of the best attributed material. It's said that he was invited to Egypt by the leader Al-Hakim, who reigned in Egypt from 996 until 1021. Alhazen was invited there because he claimed he would be able to stop the flooding of the Nile, to control the waters of the Nile. So Al-Hakim brought him in. Alhazen took a trip up the Nile. And the further he went, the more disappointed and disillusioned he got, because he realized that the lay of the land in the upper Nile was not what he thought it was. And so the flooding wasn't caused exactly by the principles he imagined. And moreover, he tells us that as he went up the Nile, he saw these immense monuments that had been built by the ancient Egyptians. And the more of them he saw, the more puny he felt. And he realized that if the ancient Egyptians couldn't stop the flooding of the Nile, he couldn't do it either. Well, he returned to Cairo and was afraid that he would be punished for his failure. Al-Hakim was known to be erratic and a man of bad temper. And so what Alhazen did, according to the story, is that he pretended to have gone insane. And he feigned madness until Al-Hakim died. And then he was back to his normal senses suddenly. He supported himself for the rest of his life in an interesting way. Once a year, he would make a copy of the Almagest, of Euclid's Elements, and of the related texts of Euclid, and sell them. And that brought him enough money to live for a year. He was connected to the mosque of Al-Azhar, where Al-Azhar University is now, for the rest of his life. So after the death of Al-Hakim, so that would be for the next 18 years.